tracking errors through types in quantum programs, and this is joint work with Kesha Haidallah and Mike Hicks, both of whom you've seen up here already today. So here's an overview of the talk, basically. So we expect that errors, particularly those errors that are introduced by gate application, but also other kinds of errors, are going to be prevalent in near-term machines and should be taken into account by the programmer, not just by some automator, because we might actually need to want to write a program that is aware of these errors, and therefore we want to be able to include them in the code that we write. So what we did is we designed a simple system to track errors in quantum programs, and we implemented that in QWIRE, and we allowed for some degree of assurance about these errors. Since I really happen to like this programming language, I'll tell you a little bit about QWIRE. So QWIRE is a small but expressive quantum circuit language. It's embedded in the Coq proof assistant, which you've seen a little bit about, which means functional language, and it's in one in which we can prove things about our programs, which is really nice. It has a linear type system, similar to Proto-QWIPR, and that enforces the no-cloning theorem. And it has a nice denotational semantics in terms of density matrices. That's convenient, but well, I won't talk about that until the very end of this talk. So what does a QWIRE circuit look like? Really, it's just this data type. I'll walk you through the main parts of it. So a circuit can either just be an output, so it outputs some wire or complex wire called P, and that wire is going to have a given type. And I'll show you what those types are on the next slide. Or it can be a gate application. And a gate application consists of three things. It consists of the gate itself, and that gate is going to have an input type and an output type. So that might be takes in a qubit, outputs a bit. It's, of course, going to have the input pattern, which we'll call P1 here. And it's going to have a continuation circuit. I'm not going to focus on dynamic lifting because it's not so important to this talk, and also because you had a nice discussion of dynamic lifting just 2 talks ago. So you saw these wire types. Well, what can they be? They can be a qubit, a bit, 1, which basically means no data and is just there for convenience, kind of, or it can be a product of 2 wire types. So, for instance, qubit, tensor bit would be a valid wire type. And all of the gates in the system have input and output wire types. So for the unitary gate, it's going to be whatever the input or output of the unitary itself is. So for C0, it's a pair of qubits. For Hadamard, it's just a single qubit. And for the others, it's the things you would expect. So init produces a qubit from nothing, basically. Nu produces a bit. Measure turns a qubit into a bit. And one thing that we tend not to think about too much, or at least we didn't think about when we designed this, is what do we actually mean when we say, oh, this thing is a qubit, right? So there are options, right? One option is that we're talking about an actual physical qubit. That's nice for controlling, small specific machines, but these things are very error prone. And if we were talking about physical qubits, our semantics wouldn't make that much sense because not accounting for errors would be something rather severe and sort of a mistake. Another possibility is we're talking about logical qubits, which consists of hundreds or perhaps thousands of physical qubits, and we assume then that it's highly error tolerant and it's regularly corrected. That would mean that our semantics make sense. We don't have to think about errors anymore. But it would also mean that we're writing programs for computers that aren't likely to exist for at least a decade or so. So the third option, and that's the one we're going to focus on here, is simple encoded qubits. So this is going to be a qubit refers to some small number of physical qubits, say 9 or 17 or 7. And that's what we call a qubit. And one example of this would be using the Shor code. So there we see the representation of 0 and 1 using the Shor code. And this is tolerant to an X error or a Z error. We can easily correct those. So how do we add errors to QWIRE? In other words, adjust QWIRE's system so that it can account for errors. Really, we only need to make one little change to our wire types. And that is, instead of having a qubit, we can have a qubit that has sort of collected on it up to k errors. And that's, we just added a natural number parameter to qubit, and now there are errors on our qubits. And one thing we're going to want to add to our gate set then, in order to be able to correct errors, is an error correcting gate, and I'm going to call that EC. So let me show you the updated now gate set. So now gates have a NAT, which say the number of errors that are introduced by that gate. Unitary application inherits its number of errors from the type of the unitary itself. So each unitary might introduce a different number of errors. C0 may be more error prone than a simple Z gate. And so that creates a gate with k errors, and the output is going to be a new set of qubits where we've incremented the error on it by k plus the number of errors coming into the gate. So we aggregate all those errors and add k to it. For initialization, I assume that you're going to specify some number of errors that are introduced. Potentially, we could be able to initialize errors, qubits for free, but that's not necessarily going to be the case. And likewise, measurement could introduce an error before it outputs a bit. Error correction itself could introduce an error. I don't think there's a way for, say, discard to introduce an error because it's taking a bit. It's between classical values. So there it's always going to be 0. And finally, we'll assume that error correction is going to produce a bit that has 0 errors in it. But that's going to be contingent on something. And that's going to be contingent on that we're doing something called fault-tolerant operations. So I'm going to tell you what that is. So this is mostly taken from Gottesman's Introduction to Error Correction. So we're going to say that an operation is fault-tolerant if, given that there aren't too many errors already on your qubits, then it doesn't introduce too many errors, and it basically performs the operation you intended. So let's make that precise. Firstly, we'll assume the existence of an ideal decoder that corrects up to t errors for some specified t. So a unitary operation would be fault-tolerant if, whenever the error coming in plus the gate's error is less than t, we know that the error coming out is going to be less than that sum. And decoding the unitary applied to some state that satisfies this limit is equivalent to applying the ideal version of the unitary to the ideally decoded quantum state. Similarly, for an error correction gate, we'll call that fault-tolerant if E out being less than our threshold, if E out is always less than our threshold, because otherwise it's not a very good error correcting gate. And if, again, the error coming in plus the gate error is less than t, implies that doing error correction and then ideally decoding is the same as just decoding the state itself, right? So obviously, these two things should be true of an error correction gate. So now that we have this notion of fault tolerance, how do we guarantee that our circuits are fault tolerant? So we're going to take advantage of QWIRE's type system itself. In particular, its type checking algorithm. So we're going to benefit here from linearity. As I've said, QWIRE has a linear type system, so everything is used precisely once. That's nice because that means that nothing is mutable here. We only have, you can't introduce an error onto a qubit. You can only consume a qubit and produce a qubit that has new amounts of error. So that makes things convenient. It kind of makes this problem simpler. But also conveniently, checking that our circuits are fault tolerant is actually an orthogonal problem to checking linearity. So we don't have to make any major changes to QWIRE's type system. So here's actually the changes. So here is QWIRE's judgment that just a gate application is well typed. And I'm not going to ask you to read all this because it's hard even for me to read it. But what I am going to ask you to look at is what we've added here. We've added k, which is the number of errors introduced, t, which is our threshold. As you saw, we altered the definition of gate slightly. And this is the one requirement that we've added for a gate application to be fault tolerant. And it's the same thing you saw earlier. It's just that k plus the sum of the input wires has to be less than our given threshold. And if we can show that this is true, then we can show that this was a fault tolerant operation. So let me give you an example of this. So here is a simple circuit that you've all seen a number of times. This is our teleportation circuit. Except I've added explicit error correction to Alice and Bob's portion of the circuit. So I'm not going to show you the definition. I'm just going to show you the types, because that's what I care about. So Bell has 2 qubits. Sorry, Bell has no input and produces 2 qubits. And those qubits, well, let's see. We're going to introduce one error via the Hadamard. That's our assumption here. And then the C0 will aggregate that error and produce another error on both of its wires. So it produces 2 errors on each of its qubits. We then have the Alice circuit, which we're going to assume that the first qubit has 0 errors on it, and the second qubit, of course, has 2, because we want to take in the Bell pair. And, well, here we're going to output bits, so there are no errors on our bits, but we are going to have to do error correction before we apply the Hadamard to avoid hitting our threshold of 3. Bob, likewise, takes in 2 bits, and that other qubit over here that already we knew had 2 errors on it, and is also going to do error correction, thereby producing a qubit that only has 1 error after the Z is applied. And then if we combine all of these together, we're going to get our teleport circuit. And it's going to take in a single qubit with no error, and it's going to output a qubit with 1 error. And that should be the same qubit modulo the error introduced to it. And how do we prove that it was fault tolerant? Well, we can just use our type checking, our old type checking procedure, and it's been augmented with a check this, simple arithmetic constraint. Last thing is we can also do type inference. So if I don't tell Coq what the type of bell is, it will infer it. For the Alice circuit, I do need to specify a tiny bit of information. That is, how many errors were on each of the 2 input wires, because it has no way of knowing that. But if I do that, it can infer the rest. The same is true for Bob. So there are 2 bits. Those don't have errors, but the qubit might. And then once it has all that information, if it wants to just compose all of those into a teleportation, we don't need to provide any information, and it infers what the input and output should be in terms of the errors accumulated. So before you ask questions of me, I have some questions for you. One is, and this is something that's been we've been thinking about, how do we reflect this error handling back into QWIRE's denotational semantics in a way that makes sense and allows us to sort of now use this to prove things about the semantics of QWIRE programs. How do we deal with decoherence errors, given that those aren't captured by gate application? Can we safely ignore them? Is there something else we can do that still fits within the parameters of a type system or something similar? And are there better ways of handling errors in some simple, pretty much automatable system in a lightweight way? So those are my questions for you. If you have questions for me, go ahead.
So I was wondering, if you had an error model, could you normalize it somehow and encode it using your natural numbers? So since your types only allow natural numbers, and if you had an actual error model where you knew that each operation, produces some amount of error, would it be possible to encode?
You mean like some probability of error?
Yeah.
So yeah, we can easily alter this to take, instead of natural numbers, probabilities, and we can aggregate those probabilities in any number of ways. So that's a very easy modification. I'm not sure how much closer gets us to a really good model of errors for any existing computer, but that's a natural extension.
And wouldn't that be easier to reflect in the model if you had a proposition?
If what?
If you had a proposition notion of error, it would make more sense somehow
It might, but you would still have to say there's, you know, you would still have to reflect it in the density matrices, and you'd have to have an alternative density matrices reflecting, you know, what the error actually is. I still don't think it gets us something that is really the kind of error model we want in our density matrix semantics.
It gets you part of it, right? You have to know what the errors, what the corruption is and the likelihood.
Yeah, yeah. So it gets us closer.
Other questions? You guys want to eat, don't you? Okay, so thank you very much for, first of all, thanks, Robert, for that nice talk.